At the beginning of the 20th century, physics stood at a strange and uncertain turning point. For centuries, scientists had believed that the laws of nature were clear, predictable, and continuous. Objects moved according to Newton's laws, forces acted in smooth and measurable ways, and the universe seemed to operate like a vast and orderly machine. Even atoms, once thought to be the smallest building blocks of matter, were imagined as solid and indivisible particles. But as experimental techniques improved, this simple picture began to break apart. Scientists studying atoms discovered that they were not solid at all. Instead, atoms contained smaller components, and their behavior did not follow the familiar rules of classical physics. Light sometimes behaved like a wave, but in other experiments it acted like a stream of particles. Energy, which had always been thought to vary smoothly, appeared to come in discrete packets. The deeper scientists looked into the structure of matter, the more the universe seemed to resist clear explanation. It was within this growing uncertainty that Niels Bohr emerged, a physicist whose ideas would help shape a new understanding of the atomic world. Niels Bohr was born in 1885 in Copenhagen, Denmark, into a family that valued both science and intellectual curiosity. His father, Christian Bohr, was a respected physiologist who studied how the body uses oxygen, and his home was often filled with conversations about science, philosophy, and the nature of knowledge. From an early age, Niels grew up in an environment where questioning ideas and exploring complex problems was encouraged. As a child, Bohr showed a calm and thoughtful personality. He was not driven by competition or speed, but by a quiet desire to understand things deeply. He often took time to reflect on problems, considering them from different angles before reaching conclusions. This patient and reflective way of thinking would later become one of his greatest strengths. He studied at the University of Copenhagen, where he quickly developed an interest in physics. At the time, physics was undergoing rapid change. New discoveries about electricity, radiation, and atomic structure were challenging long-held beliefs. Bohr was drawn to these questions, particularly the problem of how atoms were structured and how they behaved. After completing his early studies, Bohr traveled to England to work with some of the leading physicists of the time. He first joined the laboratory of J.J. Thomson at Cambridge. Thomson had discovered the electron, showing that atoms contained smaller, negatively charged particles. This discovery had already transformed the understanding of atomic structure, but many questions remained unanswered. Bohr's time at Cambridge was important, but it was not where he made his greatest progress. He soon moved to Manchester to work with Ernest Rutherford, whose experiments had revealed a new model of the atom. Rutherford had shown that atoms contain a small, dense nucleus at their center, surrounded by electrons. This nuclear model replaced earlier ideas that atoms were uniform spheres, but it introduced a serious problem. According to classical physics, electrons orbiting a nucleus should continuously lose energy as they move, causing them to spiral inward and collapse into the nucleus. If this were true, atoms would be unstable and could not exist in their observed form. Yet atoms clearly did exist. This contradiction puzzled physicists and demanded a new explanation. Bohr began thinking deeply about this problem. He was aware of another important development in physics, the work of Max Planck and Albert Einstein, who had shown that energy is not always continuous but can exist in discrete units, later called quanta. This idea suggested that at very small scales, the rules of physics might be different from those observed in everyday life. Bohr wondered whether this concept could be applied to the structure of the atom. In quiet reflection and careful reasoning, he began developing a new model. He proposed that electrons do not move around the nucleus in just any possible path. Instead, they occupy specific orbits, each with a fixed amount of energy. While in these orbits, electrons do not lose energy, which explains why atoms remain stable. This idea was radical. It suggested that at the atomic level, nature does not allow continuous motion in the way classical physics had assumed. Instead, electrons could only exist in certain allowed states, and transitions between these states involve sudden changes rather than smooth shifts. Bohr also proposed that when an electron moves from a higher energy orbit to a lower one, it releases energy in the form of light. The color or frequency of this light depends on the difference between the energy levels. This provided a direct explanation for the spectral lines observed when elements emit light, patterns that have been studied for years but not fully understood. With this model, Bohr was able to explain the behavior of the hydrogen atom with remarkable accuracy. His theory matched experimental observations and provided a framework for understanding atomic structure in a new way. Although it was not a complete theory, it marked a major step forward, combining classical ideas with emerging concepts from quantum physics. What Bohr had done was introduce a new way of thinking about nature. Instead of continuous motion and predictable paths, the atomic world followed rules that were discrete, structured, and sometimes counterintuitive. The universe at its smallest scale was not a simple machine, but something far more subtle and complex. And this was only the beginning of a transformation that would reshape physics entirely. As Niels Bohr developed his model of the atom, he was stepping into a scientific landscape that was rapidly changing but still deeply uncertain. His proposal that electrons could only occupy specific, fixed energy levels was not just a small adjustment to existing theory. It was a fundamental shift in how nature itself was understood. For centuries, physics had been built on the idea that change was continuous, that objects could move smoothly from one state to another. Bohr's model suggested something very different. At the atomic level, change could occur in sudden steps, with no intermediate states allowed. This idea challenged intuition. It solved problems that had puzzled scientists for years. One of the most important successes of Bohr's model was its ability to explain the spectrum of hydrogen. When hydrogen gas is heated or energized, it emits light at very specific colors rather than a continuous range. These colors appear as distinct lines when passed through a prism, forming what is known as a spectral pattern. Before Bohr, scientists could measure these lines with great accuracy, but they could not fully explain why they appeared in such a precise and orderly way. Bohr's theory provided the answer. According to his model, electrons in a hydrogen atom can exist only in certain allowed energy levels. When an electron jumps from a higher level to a lower one, it emits a specific amount of energy in the form of light. Each possible transition corresponds to a particular wavelength, producing the distinct spectral lines that have been observed in experiments. The agreement between his calculations and the measured spectral lines was striking. For the first time, a theoretical model could explain these patterns with precision. This success gave Bohr's ideas strong credibility, even though they were difficult to fully accept from a classical perspective. His model worked, and in science, predictive accuracy carries great weight. However, Bohr himself understood that his theory was not complete. While it explained hydrogen very well, it struggled to account for more complex atoms with multiple electrons. The model relied partly on classical ideas of electrons orbiting the nucleus, combined with a new concept of quantized energy levels. It was a bridge between two worlds, not yet a fully consistent theory. Still, it opened the door to a deeper exploration of atomic physics. As Bohr returned to Copenhagen, he began building an environment where these new ideas could be developed further. He established what would become the Institute for Theoretical Physics, a place where scientists from around the world could gather to discuss and explore the emerging field of quantum theory. The Institute became a center of intense intellectual activity, filled with conversations, debates, and collaborative thinking. Bohr's role was not only that of scientist, but also that of a guide. He had a unique way of thinking, often speaking in careful, reflective language, exploring ideas from multiple angles before reaching conclusions. His discussions with other physicists were known for being deep and sometimes challenging, as he encouraged others to question assumptions and think beyond traditional frameworks. During this time, the field of quantum physics began developing rapidly. Scientists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac were working on new mathematical formulations that described the behavior of particles at the atomic scale. These developments went beyond Bohr's original model. replacing the idea of fixed orbits with more abstract descriptions of probability and wave functions. Bohr played a central role in interpreting these new theories. One of his most important contributions during this period was the concept of complementarity. This idea addressed one of the most puzzling aspects of quantum physics, the fact that particles like electrons and photons sometimes behave like waves and sometimes like particles. In classical thinking, something must be either one or the other. But experiments showed that both descriptions were necessary to fully understand atomic behavior. Bohr suggested that these seemingly contradictory properties were not mutually exclusive, but complementary. According to this view, different experiments reveal different aspects of reality, and no single description can capture the full nature of quantum systems. Wave behavior and particle behavior are both real, but they cannot be observed simultaneously in the same way. Instead, they represent different perspectives on the same underlying phenomenon. This idea required a new way of thinking about reality itself. It suggested that at the deepest level, nature does not conform to simple, intuitive categories. Instead, it must be understood through a combination of perspectives, each revealing part of the truth. This was a profound philosophical shift, extending beyond physics into questions about knowledge and observation. Bohr also emphasized the role of measurement in quantum systems. In classical physics, objects have definite properties whether or not they are being observed. But in quantum physics, the act of measurement plays a crucial role. The state of a system is not fully defined until it is observed, and the process of observation itself influences the outcome. This idea challenged traditional assumptions about objectivity and raised deep questions about the relationship between observer and reality. These discussions were not always easy. Even among leading physicists, there were disagreements about how to interpret quantum theory. One of the most famous debates took place between Niels Bohr and Albert Einstein. Einstein was uncomfortable with the probabilistic nature of quantum mechanics, believing that a deeper, more deterministic explanation must exist. He questioned whether the theory was complete. Bohr, on the other hand, defended the new framework. Their debates, often carried out through discussions and written exchanges, became some of the most important conversations in the history of science. They were not simply arguments, but explorations of fundamental questions about how the universe works. Through these exchanges, the ideas of quantum mechanics were tested, refined, and better understood. As the years passed, Bohr's influence continued to grow. He was not only contributing to the development of quantum theory, but also shaping the way scientists thought about it. His institute in Copenhagen became a gathering place for some of the greatest minds in physics, a place where new ideas were explored with depth and seriousness. The atomic world that Bohr helped reveal was no longer simple or predictable in the classical sense. It was a world governed by probabilities, discrete states, and relationships that depended on how they were observed. It required new language, new mathematics, and a willingness to accept that reality at its smallest scale might not behave in ways that align with everyday experience. And yet, through all this complexity, Bohr continued guiding the search for understanding, helping to build a framework that would define modern physics. As quantum theory continued to develop in the 1920s, Niels Bohr found himself at the center of one of the most profound transformations in the history of science. What had begun as an attempt to understand the structure of the atom was now expanding into a complete rethinking of how nature behaves at its most fundamental level. The familiar certainty of classical physics was giving way to a new framework where probability, uncertainty, and observation played essential roles. At the Institute for Theoretical Physics in Copenhagen, Bohr created an environment unlike any other in the scientific world. It was not simply a place for formal lectures or isolated research. It was a space where ideas were constantly discussed, questioned, and reshaped. Physicists from across Europe traveled there to work with Bohr, bringing with them new theories, new equations, and new ways of thinking. The atmosphere was intense, but deeply collaborative. Scientists would spend long hours in conversation, sometimes walking together, sometimes sitting in quiet rooms filled with chalkboards covered in equations. Bohr himself was known for engaging in long, thoughtful discussions. He often spoke slowly, carefully choosing his words, exploring different possibilities before arriving at a conclusion. For those around him, these conversations could be challenging, but they were also deeply influential. One of the central ideas emerging during this period was the concept of uncertainty. Werner Heisenberg, one of the young physicists working closely with Bohr, developed what became known as the uncertainty principle. This principle stated that certain pairs of physical properties, such as position and momentum, cannot both be known with complete precision at the same time. The more accurately one is measured, the less precisely the other can be determined. This was not simply a limitation of measurement tools. It was a fundamental property of nature. Bohr recognized the importance of this idea and incorporated it into his broader interpretation of quantum mechanics. He saw uncertainty not as a flaw in the theory, but as an essential feature of how the atomic world operates. It reinforced his belief that classical concepts could not fully describe quantum phenomena, and that new ways of thinking were necessary. Another key development during this time was Schrödinger's wave mechanics. Erwin Schrödinger introduced a mathematical equation that described particles not as points moving along definite paths, but as wave-like distributions spread out over space. This approach provided a different way of understanding quantum systems, one that emphasized continuous wave behavior rather than discrete jumps between orbits. At first, this seemed to conflict with earlier ideas, but Bohr saw something deeper. He understood that these different approaches were not necessarily contradictory, but complementary. Wave mechanics and particle descriptions both captured aspects of reality, even though they appeared incompatible when taken alone. This reinforced his concept of complementarity, the idea that multiple perspectives are required to fully describe quantum phenomena. Within this framework, the behavior of particles could not be reduced to a single, simple picture. Instead, understanding required accepting that nature can exhibit different characteristics depending on how it is observed. This way of thinking was not easy to accept. It challenged deeply held assumptions about reality, objectivity, and the nature of scientific description. For many physicists, including Einstein, the idea that outcomes could be fundamentally probabilistic rather than determined by precise laws was difficult to reconcile with the tradition of physics. The debates between Bohr and Einstein became increasingly significant during this period. Einstein presented a series of thought experiments designed to show that quantum mechanics might be incomplete. He argued that there must be hidden variables, underlying factors not yet understood, that could restore certainty and determinism to physics. Bohr responded to each challenge with careful reasoning. He showed that the conclusions of quantum mechanics remain consistent, even when examined through Einstein's thought experiments. Rather than revealing flaws in the theory, these discussions often strengthened the understanding of its principles. Bohr maintained that the probabilistic nature of quantum mechanics was not a temporary limitation, but a fundamental aspect of reality. These debates were not about winning or losing. They were part of a deeper effort to understand the nature of the universe. Through these exchanges, the philosophical foundations of quantum mechanics became clearer. Scientists began to accept that at the smallest scales, reality does not behave like the familiar world of everyday objects. Instead, it follows rules that are subtle, interconnected, and sometimes counterintuitive. Bohr's influence extended beyond specific theories. He shaped the way physicists approach problems, encouraging them to think carefully about the relationship between observation and reality. He emphasized that scientific descriptions are not direct representations of an independent world, but tools that help us understand and predict phenomena. During this period, Bohr also contributed to the understanding of atomic structure beyond hydrogen. While his original model had limitations, it inspired further research into how electrons are arranged in more complex atoms. These studies eventually led to a deeper understanding of chemical properties and the behavior of elements, connecting quantum physics with chemistry in meaningful ways. As the years progressed, quantum mechanics became more widely accepted. It provided accurate predictions for a wide range of experiments and became the foundation for many areas of modern science. The work done in Copenhagen and other centers of research helped establish a new framework that would influence physics for generations. Through it all, Bohr remained a central figure. He was not only a contributor to the theory, but also a guide in interpreting its meaning. His ideas about complementarity, uncertainty, and the role of observation helped define how scientists understand the quantum world. What had once seemed like a collection of strange and disconnected results had become a coherent, though deeply complex, picture of reality. And at the center of this transformation stood Niels Bohr, quietly shaping one of the most important intellectual revolutions in human history. As the decades passed, Niels Bohr's role in science continued to evolve, moving beyond the early development of quantum theory into a position of global influence, both intellectually and politically. The ideas he had helped shape were no longer limited to academic discussions. Quantum mechanics was becoming the foundation of modern physics, influencing chemistry, materials science, and eventually technologies that would transform everyday life. Yet at the same time, the world around Bohr was entering a period of profound instability. In the 1930s, political tensions across Europe began to rise. Scientific collaboration, which had once freely crossed national boundaries, was increasingly affected by the growing influence of authoritarian regimes. Many scientists were forced to leave their home countries, seeking safer places to continue their work. Bohr's Institute in Copenhagen became a place of refuge for some of these displaced thinkers, reflecting his commitment not only to science, but to the broader community of researchers. During this period, Bohr also turned his attention to the structure of the atomic nucleus. While his earlier work had focused on electrons and atomic behavior, new discoveries were revealing that the nucleus itself was complex and dynamic. In 1939, Bohr contributed to the understanding of nuclear fission, the process by which a heavy atomic nucleus can split into smaller parts, releasing a large amount of energy. This discovery would soon have consequences far beyond the laboratory. As the Second World War began, the implications of nuclear physics became impossible to ignore. The possibility of building powerful weapons based on nuclear reactions created urgency and concern among scientists. Bohr, like many of his contemporaries, understood both the scientific significance and the potential danger of these developments. When Denmark was occupied during the war, Bohr's situation became increasingly difficult. Due to his background and his connections within the international scientific community, he was at risk under the occupying regime. In 1943, Bohr was forced to leave Denmark. In a quiet and carefully arranged escape, he was transported to Sweden and later to the United Kingdom, eventually making his way to the United States. There, he became involved in discussions related to the development of nuclear weapons. Although he contributed his knowledge, Bohr remained deeply concerned about the ethical implications of such work. He believed that the power unlocked by nuclear physics required careful international cooperation and openness. Bohr argued that secrecy and competition between nations could lead to dangerous outcomes. He advocated for transparency and dialogue, hoping that scientific knowledge could be used responsibly rather than as a source of conflict. His views were not always accepted in the political climate of the time, but they reflected his broader philosophy about science as a shared human endeavor. After the war, Bohr returned to Copenhagen, where he resumed his work at the institute he had helped build. The post-war period marked a time of reflection as well as continued scientific progress. Quantum mechanics had firmly established itself as a central theory in physics, and its applications were expanding rapidly. Technologies based on quantum principles, including early forms of electronics and later developments in computing, began to emerge, showing how abstract ideas could lead to practical innovations. Bohr remained active in both scientific and philosophical discussions. He continued exploring the deeper meaning of quantum theory, particularly the relationship between knowledge, measurement, and reality. His idea of complementarity extended beyond physics into broader reflections on how seemingly opposing perspectives can both be necessary to understand complex systems. Whether applied to science, philosophy, or even human thought. This principle emphasized balance and the acceptance of multiple viewpoints. Throughout his life, Bohr maintained a quiet and thoughtful presence. He was not driven by recognition or public attention, but by a genuine desire to understand and to help others understand. His conversations, often long and carefully reasoned, influenced generations of physicists. Many of the leading scientists of the 20th century spent time at his institute, carrying forward the ideas that have been shaped there. Niels Bohr died in 1962 at the age of 77. By that time, the world of physics had been completely transformed. The atom, once thought to be simple and indivisible, was now understood as a complex system governed by quantum laws. The theories developed during Bohr's lifetime had not only explained the behavior of matter at the smallest scales, but had also led to technologies that reshaped communication, medicine, and industry. His legacy is both scientific and philosophical. Scientifically, he helped establish the foundations of quantum mechanics, contributing key ideas that remain central to the field. Philosophically, he challenged the way people think about knowledge and reality, showing that understanding often requires accepting complexity rather than seeking simple answers. The world revealed by Bohr's work is not one of certainty in the traditional sense. It is a world where outcomes are described by probabilities, where observation plays a role in defining reality, and where multiple perspectives are needed to grasp the full picture. This vision of nature, though difficult to fully comprehend, has proven to be remarkably accurate in describing the behavior of the universe at its most fundamental level. From the quiet halls of Copenhagen to the global stage of scientific discovery, Niels Bohr helped guide one of the greatest intellectual shifts in human history. His work reminds us that progress often comes not from forcing the world to fit our expectations, but from being willing to rethink those expectations entirely, allowing new ideas to reshape our understanding of reality itself.